I will start class in 2 minutes. I'm waiting for the students. I hope I'm audible. Only 15 participants. Hello. Good afternoon. Yeah, A section. A section online ಇದೆಯಲ್ಲ ಅವರು ಲಿಂಕ್ ಶೇರ್ ಮಾಡ್ತಾರೆ. ಅಲ್ಲ ಅವರು ಮೆಸೇಜ್ ಮಾಡ್ತಾರೆ ಬಿಡಿ. ಯುವರಾಜ್ ಅಂತ ಅಲ್ವಾ ಅವರು ಅವ್ರು ಮಾಡ್ಕೊಂತಾರೆ ಬಿಡಿ. Okay, I think I can't get more than 25 today. Okay, let me start the class. In the last class, we were discussing about the lasers. Okay, in that, even in particular, we have discussed about the expression for energy density of laser. Okay, 1 minute, I will share. I mean, can you see this PPT slide? Please raise your hand. Module 3 laser. Can you see this? Okay, thank you. Thank you. Now I will change the slide. Now, please someone write in the chat box. Can you see this comparison between normal light and laser light? Please someone write in the chat box. Can you see this slide? No, sir. Okay. Let me share once again. Okay, okay. I will share. Now, can you see? Please raise your hand. Can you see? Okay. 4 participants raise hand. Thank you, thank you, thank you. I think now it is visible. Please someone write in the chat box. Can you see this comparison now? Okay, thank you. Thank you, I think, thank you. Now, in the last class, we have compared normal light with laser light, which is not at all interesting from the point of view of examination. Okay. And then I have explained about, okay, I have explained about 3 different processes which take place in a laser system. That is induced absorption. Okay. Induced absorption is nothing but absorption of radiation from the ground state, and hence the excitation of atom to the higher energy state. Okay. This I think you have observed. And also I have explained the concept of spontaneous emission. In the spontaneous emission, the atoms which is already present in the excited state comes to the ground state by emitting a photon. Okay. This takes place on its own. Therefore, it is known as spontaneous. Okay. And here there is no amplification of radiation takes place. That means whatever energy actually goes in, that will come out. That's it. Therefore, there is no amplification observed. But to amplify, what is the meaning of amplification? Amplification is getting more photon. Okay. For example, if I incident one photon, I should get at least two photons as output. That is known as amplification, right? Therefore, here you can see I have explained the stimulated emission as well, right? In the stimulated emission, the atom actually exists in a metastable state. Okay, the atom will be there in a metastable state where the atom have the higher lifetime in the excited state. Okay, atom will be there in the metastable state slightly greater than the ordinary excited state. Okay, for these type of atoms, you require a external aid. You require a incident photon. If you incident this photon, then only this atom comes to the ground state. Now, while coming to the ground state, it will emit not only one photon, but two photons. One is the incident photon itself, another one is the stimulated emitted photon. Okay, stimulated photon. And therefore, I'm incidenting one photon and I'm getting two photons back. This is the meaning of amplification of radiation. Okay, these are all explained in the previous class. And then I have actually showed the derivation of expression for energy density. Okay, I just want to remind once again, energy density means I require energy to excite the atom, okay, in the induced absorption phenomena, and also I require the energy in the stimulated emission phenomena. Therefore, I have to obtain expression for energy density. Okay, energy density is represented by U mu d mu, okay, or U mu. U mu represents the energy density of incident photons of frequency mu. Okay, here you can see there is a photon and the energy per unit area falling on the material is known as U mu. And I have also said the rate of absorption is directly proportional to the energy density of the incident photon as well as number of atoms in the ground state. Okay, if there are no atoms in the ground state, forget about the excitation. Therefore, N1 is important. Also, if you don't incident photon, if you don't have this U, then there will be no excitation. Therefore, rate of absorption depends on these two factors, and constant of proportionality is known as Einstein's coefficient, right? That is, I have represented with B12 symbol. And then I have similarly obtained expression for rate of spontaneous emission. Here, spontaneous emission doesn't require any incident photon. It will, atom in the excited state on its own will come back to the ground state. Therefore, I just have N2, that is rate of spontaneous emission is directly proportional to N2 only. And the constant of proportionality is again 1 nu Einstein coefficient. Similarly, in the in the stimulated emission, rate of stimulated emission directly proportional to incident photon and number of atoms in the excited state. This is obvious, okay? The stimulated emission requires incident photon, right? Therefore, these are the two factors on which rate of stimulated emission depends, okay? Now, the constant of proportionality is the new Einstein's constant, B21, Einstein's coefficient, okay, B21. And also I have argued rate of absorption must be equal to rate of stimulated emission plus rate of spontaneous emission. Okay, you just substitute all the mathematical terms here and you will see this kind of a equation. Okay, rate of spontaneous rate of induced absorption is equal to rate of spontaneous emission plus rate of stimulated emission. And doing some algebra, I can actually show that the expression for U nu energy density will be like this. And again, simplifying that by taking some factors out, then you will get this type of equation. And in that equation, the number of atoms in energy level N1 and number of atoms in the energy level N2 will be related by Boltzmann's law. This is a new concept you have to remember on your own, and substitute N1 by N2 in the equation 4. Here you will have N1 by N2, substitute it with e power E2 minus E1 by kT. E2 minus E1 is nothing but delta E. right? Delta E, that is energy difference between E2 and E1. And you know that according to Bohr's theory, E2 minus E1 is the energy of the photon, h nu. Okay. And substitute this N2 minus N1 in the equation, and you will find this equation 6. Okay. Now this equation 6 is compared with Planck's radiation law. Okay. Planck's radiation law you have studied in module 2. And if you substitute, make comparison, then you will find actually B12 is equal to B21. By comparison itself, you can see this. Okay. And finally, you will write the expression for energy density as U nu is equal to A divided by B into E power h nu by kT minus 1. Okay. Here A and B are the Einstein's coefficients. This thing you have to remember. This is actually done in the last class. Please practice this derivation. This is very important from the point of view of second internals. Okay. If I am the paper setter, I will definitely give this question. Okay. Please practice this. Today, I will discuss two more important concepts in the laser module. One is construction and working of carbon dioxide laser. And second one is construction and working of semiconductor laser. Okay. In the key bunch also, you will have semiconductor lasers, right? That obvious we have, nowadays we use lasers even in key bunches. That is the direct, not so useful application of laser using in key bunch, right? And those lasers are nothing but the semiconductor lasers. Now, in this class, I will also discuss about the construction and working of semiconductor laser. Okay. Before that, I will just want to share few slides of notes that I have actually given to you. I will show in a moment. There are few minor questions which will arise in module 4. Okay. I just want to throw some light on those minor questions. Please watch this PDF. Can you see this one? Please raise your hand. Can you see this PDF module 4 laser? Okay, thank you. Participants are able to see. Okay, thank you. Now I will explain few things which are important in the examination. Of course, for the 6 marks, they will ask you to write a note on induced absorption, spontaneous emission, and stimulated emission. You have to stop up to this point. Okay. If they ask this question, explain induced absorption, stimulated absorption, and stimulated emission and spontaneous emission. Up to here, you have to write. And then the next concept is expression for energy density in terms of Einstein coefficient. This will be for 8 marks, 8, 7, 6, whatever may be. Okay. This is a very important question. You have to start with here. Okay. And you have to write up to this point. U nu is equal to A divided by B into E power h nu by kT minus 1. Okay. This is the next important question. Then there are few minor questions for 4 marks. Okay. That you have to read. First question is requisites for, requisite of a laser system. Okay. Requisite means if you assume that you are going to construct a laser, then what are the 3 essential things you have to brought with you? The first essential component is the pumping action or pumping mechanism. Okay, you have to excite the atoms to the higher energy levels, right? To do that, you have to use one excitation source. Okay, suppose if you have a project on constructing a laser, then first thing you have to go for is the excitation source. Okay, there are 3 types of excitation sources available. One is electrical pumping. Second one is photon. What is that? Optical pumping, and the third one is chemical pumping. Okay, these are the 3 mechanisms which are used to excite the atom from the ground state. Okay, now I hope you remember exciting atom from the ground state means you are actually supplying energy to the electrons of the atom. If the electron absorbs energy, then atom itself is assumed to absorb the assumed as absorb the energy. Okay, Absorption of or excitation of atom is somewhere near to excitation of electron. Okay, and I will explain actually uh, this mechanism of pumping later, which is not required. You just have to mention this. Okay, then the next important component for a laser is the medium. Medium is, for example, in the semiconductor laser, semiconductor itself is the medium, gallium arsenide material, or in the case of carbon dioxide laser, carbon dioxide itself is the active medium. Okay, I hope you can understand this. And next one is the laser cavity. Laser cavity means the space, the envelope in which you are actually going to fill this active medium. Active medium means, for example, carbon dioxide laser. Carbon dioxide will be the active medium. You have to fill this carbon dioxide into the laser cavity. Okay, laser cavity is the envelope, or it is the vessel into which you are actually filling the material. Okay, for example, semiconductor material, gallium arsenide, you have to fill it in the laser cavity. These are the three important requisites for laser system. Okay, you have to make the arrangement of all these three things. Okay, why I am stressing this question is there is one more question which is very near to, which will again mention all these things, and this is actually listed as a different question. Here they will ask you to write the condition for laser action. Okay, previously I have explained about the requisites for laser system, and there is one more question which asks you to write the condition for laser action. These two things are appear as similar, but they are different. Requisites, in the requisites for a laser system, we actually list out the materials required. Okay, we list out the materials required, and in the condition part we actually discuss about the mechanism. Okay, you have to understand this thing, otherwise you will lose 4 marks very easily. I don't know why they have actually splitted the syllabus like this, but this is a very important question. A requisite for laser system is different from necessary condition for laser action. These are the two different questions. In the earlier years, in the previous years, I have seen few students making this mistake. If I ask the question on requisites, they will write the necessary conditions. If I ask the question on conditions, they will write the requisites. Okay, you should not make that mistake. Therefore, I am stressing this. Okay, be careful. Requisites are the materials. Conditions are the conditions are the mechanisms. Okay, let me repeat once again. Requisites are the excitation source, active medium, and laser cavity. These are the materials you have to make sure. Okay, the excitation source is the energy provider. Okay, this is the energy provider to the atoms. Okay, and most common energy provider is the optical pumping. Optical pumping means, for example, if you are constructing a carbon dioxide laser, you have to fill the carbon dioxide laser into the gaseous or fiber envelope. On the top of that, you have to wrap some flashlight tubes. Okay, I think you have seen this optical fiber materials which can be wrapped on the glass material. Okay, this optical fiber will actually gives out flashes, and these flashes will be absorbed by the carbon dioxide atom, and then these carbon atoms will be get excited. Okay, that means I can excite carbon dioxide molecules by applying light flashes. Okay, I'm giving just an example. Okay, ruby laser and flash lasers, and there are variety of lasers are there, and in few they use this optical pumping mechanism. They will wrap a additional photon source on the material, and that photon source will excite the atoms of the carbon dioxide or semiconductor material. Okay, and this is all about excitation source. Okay, And in electrical pumping, they just connect a anode and a cathode into the laser cavity, and they will apply very high voltage. Okay, when you apply very high voltage, the electrons from the cathode starts to move towards the anode. While moving towards anode, they will hit these carbon dioxide molecules, and carbon dioxide molecule will be excited. Okay, that is the meaning of electrical pumping. Okay, you can use either photon source, or you can directly excite the atoms using current, electricity. Okay, and the next thing is the active medium. Active medium I have already mentioned. You can see here the usual laser will look like this. This rectangular thing is the envelope. This may be is a glass envelope, rectangular glass, within which I am going to fill the active medium, for example carbon dioxide. Okay, and this is all about active medium. And then laser cavity is nothing but this rectangular material made up of glass or fiber, which is enclosed with mirrors. On either side you will have a mirror. Okay, you can see this is also mirror and this is also mirror. One side I have fully silvered mirror. That means just try to imagine, if I excite the atoms inside this laser cavity, these atoms will de-excite by emitting photons, and to get collimated rays or to get highly directional laser light, I have to, the emitted photons will be in various directions. They will not travel in the straight line. What I have to do is I have to give a direction to this laser by impacting the photons on the mirror. The photon which is generated inside the active medium will get reflected by these mirrors, and they will come out in a straight line. Okay, I hope you know laser will travel in single direction. That is known as directionality of laser, right? To achieve this directionality or collimated nature of photons, what I have to do is I have to reflect the stray photons which are not in the straight line. I have to reflect them back and forth, and finally I have to emit them in a single direction. To do that, to do these reflections, I require mirrors at the ends. Okay, and one mirror is fully silver. That means it will produce 100% reflection, and the other mirror is partially silvered. Okay, partially silvered means it will transmit few photons and it will reflect few. Okay, and in that way I will get directionality. Okay, the light coming out of this part will be in a straight line direction. Okay, this is all about laser cavity. And also the length of the laser cavity is actually made in such a way that let us imagine there is a particle which is excited here, and it will de-excite by emitting a photon. Okay, this is a mirror here, and here there is a partially silvered mirror. Okay, this light ray must travel towards this mirror. Okay, and this is moving towards right side. Okay, this light ray is actually emitted by a particle, and this light ray will move towards this mirror, and then it will reflect back. Okay, it will hit the mirror and it will reflect back, and therefore we have two light rays inside the laser cavity. One is the light moving towards right, another one is the reflected light moving towards left. Again, at left I have a mirror, and therefore again I will get a light ray. Now, what is the aim of constructing this laser cavity is I must get a constructive interference between these two lights. The light which is going towards the right should constructively undergo interference with light moving towards left. Okay. To achieve that, I have to fix the distance to a suitable length. Okay, I have to fix this distance, or I have to design my laser cavity in such a way that the incident photon and the reflected photon should constructively interfere, and I should get a good intensified laser light. Otherwise that I may get destructive interference and you may not see a laser. Okay, what will happen with destructive interference? Crust of one photon will fall on trough of other photon, and that will nullify the intensity, right? That should not happen. Okay, that is the way. I mean, in that way, I have to design the length L of the laser cavity. Okay, that is, crust of one light ray must fall on crust of other light ray. Okay, this is the condition. This is the length L of the cavity. Okay, these are the three requisite things for having a laser. Okay, materials: pumping source, active medium, and laser cavity. Okay, this is a question for 4 marks. And now I will explain what are the conditions for laser action. Okay, the first condition is the population inversion condition. Population inversion means to get higher amount of intensity, you should understand number of atoms in the excited state must be greater than number of atoms in the ground state. Okay, that is known as population inversion. If you don't have enough atoms in the excited state, then you will not get a intense laser light. Therefore, to get this laser, we must have population inversion. Okay, the excited state atom should be more in number than the ground state atom. Okay, that I have explained here. To achieve that, we actually make use of 3-level laser. Okay, one is the ground level, the other one is the ordinary excited level, and the next one is the metastable level. Okay, now I think I should show the PPT. So just see this slide. Okay, let me show population inversion. Okay, here you can see I have already said ground state will have unlimited lifetime. What is the meaning of that? Ground state having unlimited lifetime. That means naturally atoms will be observed in the ground state, right? Atoms will on its own will stay in the ground state. If you don't supply any external energy, the atom will not go to the excited level. Therefore, for a long time, atom will be there in the ground state. That is known as unlimited lifetime of ground state. Okay, and the lifetime of ordinary excited state will be of the order of 10⁻⁹ seconds. That is, if I excite the atom from E1 to E3, this E3 is a ordinary excited state. The atom there will come back to the ground state within nanosecond, which will not help us in obtaining laser. Therefore, we make some arrangement, we add some impurity, and we insert one more energy level in between E1 and E3. And this is a excited state, but having higher lifetime. Okay, it will have a lifetime of the order of 10⁻³ seconds, that is millisecond. Okay, now you can ask, this is also not so big, right? We cannot even feel the millisecond. What is the use of having this E2 here? You just compare this metastable state with the lifetime of excited state. Excited state will be there for 10⁻⁹ seconds, and whereas metastable state will be there for 10⁻³ seconds. Make comparison between them. You will find there is a 10⁻⁶ second gap between energy gap. I mean time interval gap between metastable state and excited state. 10⁻⁶. That is, metastable state is 10 lakh times more stable than excited state. 10 lakh times more stable. Okay. Now, the atom which goes to this E2 will help us in obtaining this population inversion. Okay, for a moment, what happens is the number of atoms in this E2 level will be more than number of atoms in E1 level. That is known as population inversion. Okay, I have one more picture to explain. You can see if I pump these atoms in the ground state, they will go to E2 or E3, ordinary excited state. From there, they will fall back to E2, which is a metastable state. And in this step 3, you can see the number of atoms in E2 will be more than number of atoms in E1. And thus, we say that we have achieved population inversion. Okay. And the next important condition for obtaining laser action is the metastable state itself. Okay, there are two important mechanisms you have to understand, and they are known as condition for laser action. One is population inversion, another one is metastable state. That's it. Okay, I will stop class right now. Okay, in this class, I have actually discussed about 4 marks, two 4 marks questions. One is requisites for laser action. There are 3 materials which are required. One is excitation source, active medium, and laser cavity. And the second one is what are the 2 important mechanisms or conditions for laser action. One is obviously population inversion, and the second one is the concept of metastable state. Okay, these 2 are the condition for laser action. Don't confuse yourself. Just try to remember the conditions and requisites separately. Okay, don't mix them. I think I should stop the class right now. Thank you very much for the participation. In the next class, I will explain the construction and working of carbon dioxide laser and construction and working of semiconductor laser. Both of them are 8 mark questions. Okay, very important from the point of view of examination. If you have any doubts, please ask me, and I will do extra classes if required. Okay, I can repeat in the offline mode also. Okay, but it is only on demand. If you have understood, I don't repeat it. Okay, you can read on your own. I will end the class right now. Thank you very much.